Okay, so we have described these two algorithms, depth first search and breadth first search. What is the difference between these two algorithms? Depth first search treats open as a stack, last in first out. Breadth first search treats open as a queue, first in first out, and we have a feel of how they generate different search trees and explore them in a different fashion. We already saw in the last session that breadth first search seems to have one advantage, that it will not go into infinite loops, even if you are not checking for nodes enclosed, that it will eventually find a path to the goal. So, let us do an analysis of both the search algorithms and try to understand how they fare in terms of various properties of search algorithms that we will be interested in. So, we have seen this behavior, I think. If it is a small search tree, as you can see, it is on the left hand side, there is a branching factor of 3, and every node has 3 neighbors, and the search tree, as you can see, grows exponentially. That is something that we will be worried about. The first level has 1 node, which is only the start node, the next level has 3, the third level has 9, the fourth level is 27. So, it grows exponentially, and we will see that that is going to be something of concern for search algorithms. But at the moment, we are more concerned with what is the order in which they inspect nodes, and the order is shown on the right here, both for depth first search and breadth first search essentially, and we have kind of informally discussed this already. So, when the two searches pick the fifth node, so there we have seen already fourth node have been picked, and the fifth node is shown in green in both the diagrams. One is here and the other is here. You can see that the fifth node is at different levels to start with. For breadth first search, it is closer to the source, and for depth first search, it is farther from the source. And they have explored the earlier nodes in a different order. By the time depth first search picks the fifth node, it has already finished with the previous level. So, it has seen all the nodes on the previous level. That is not the case in depth first search. So, in that sense, their behaviors are different. We have already said that depth first search dives down into the search tree, and breadth first search is conservative, staying as close to the source as possible, or as close to the start as possible. So, what should be the running time? How long will each of these algorithms take to find the goal node essentially? So, in this schematic diagram, I have drawn this as something which looks like an exponentially growing search tree, and since you know the behavior of these two algorithms by now, we can see that the left hand side shows a goal node, which it will depth first search will find faster essentially. So, supposing there are 2 goal nodes in this search tree, it is possible that they occur in this thing, 2 different locations in the graph, or there are 2 different paths to the goal node. Depth first search will find one path if it is closer to the left hand side of this search tree, whereas breadth first search will find that path to the goal node which is closest to the start node essentially. So, remember that how does depth first search work? It goes down this path, then it backtracks, tries it and tries it, and that is the behavior of depth first search. It goes down, when it runs into a dead end, it backtracks. So, we are assuming that the search tree is a constant total depth. This could happen, for example, if you are solving the n queens problem, because the depth would be n. You try the first queen, the second queen, the third queen and so on. And the last one would be the nth queen. I mean, just to illustrate that point. Breadth first search, on the other hand, starts from the root, goes down the first level, then goes down the second level, then goes down the third level, fourth level and so on, and eventually it will find this node earlier if it is closer to the start node essentially, irrespective of what order. See, the order in which we are exploring the nodes depends on the order in which we are move gen function is giving to us nodes essentially, because that determines the order in which you add them to open essentially. But in general, we can observe that if it is closer to the start node, breadth first search will find it closer, but if it is generated in a branch which occurs earlier, then depth first search will find it faster. So, let us worry about let us try to discuss this a little bit more rigorously in terms of time complexity. So, we assume that there is a constant branching factor. So, we are looking at the search trees at this stage of B. So, B is a branching factor and assume that the goal occurs somewhere at depth D essentially. So, the time complexity can be measured in terms of the number of nodes inspected by each search. So, because it spends some time looking at each node, it takes it out from open, inspects it, adds its children to open and then takes out the next node. So, the number of node it inspects can be seen as a measure of time complexity, and we will call these two numbers n for DFS or n for BFS essentially. So, they let there be the number of nodes inspected by these two search algorithms. So, if the node, and we have assumed that the goal occurs somewhere at depth D, this is just for the sake of analysis. If the node occurs at the leftmost edge, then you can see that depth first search would have inspected D nodes, the start node, the node at level 1, level 2 and so on and up to the level 3. Whereas, breadth first search would have inspected this entire tree before it would have inspected the entire tree up to the previous level. Remember that it goes like this. It would have finished doing all those things and then it would have picked up this node. And so, the number of nodes that it would have inspected is whatever 1 plus 1 plus b at this level, b square at this level, b cube at this level, and eventually that will come down to this expression, which is for the summation of from 1 up to b raised to n minus 1, b raised to d minus 1. What about the other end? Supposing the goal node was at the rightmost end of this thing, in which case both the search algorithm will inspect the entire tree and the number of nodes in the tree are b raised to d plus 1 minus 1 whole thing divided by b minus 1. So, which one is better? So, on the average, if we sum up for depth first search, we have two components. One is d plus 1 if it is on the leftmost end and the other is this figure which is on the rightmost end, and for large branching factor and large depth you can assume that this approximates to b raised to d by 2 essentially. So, it is exponential. The important thing to observe is that it will look at an exponential number of nodes essentially. For breadth first search also we do the same thing, we take the expression for the left end, okay, that should include that, and the expression for the right end, and then simplify it, remove constants and so on and so forth, and what we get is something not very far from there, which is b raised to d into b plus 1 divided by 2 into b minus 1. So, if you look at the ratio of the two, the number of nodes inspected by breadth first search is more than the number of nodes inspected by depth first search, but only by a factor of b plus 1 divided by b minus 1. How much is that factor? Supposing branching factor is 10, that means 11 by 9 times more essentially. So, the larger the branching factor, the closer their time complexities will become, but the important fact is that they are exponential in nature, and as computer scientists we do not like algorithms which run into exponential times. So, we will need to do something about that. What about the size or space complexity? So, if we measure space complexity as the size of open just as an approximation, then you can look at this tree where blue are closed nodes and the blank nodes are open nodes. Both of them start with the same kind of search tree, but as depth first search explores it, you can see that the number of open nodes is not growing very rapidly as you go down deeper and deeper. Why is that? That is because as you go down the depth, at every level DFS adds B minus 1 nodes. It generates B nodes and picks one of them, and the remaining B minus 1 are added to open. So, with this branching factor of 2, you can see that it is added 2 nodes here, it is added 2 nodes here, it added 2 nodes here, out of which it picked that one, and at every stage it is adding basically 2 nodes essentially. And as in fact, as it sweeps from left to right, then that 2 will also get reduced later to 1 and so on. So, what do we see here? We see that the size of open for depth first search grows linearly with depth. Why linearly? Because at every level, as it goes deeper into the search space, it adds a fixed number of nodes, which is B minus 1 number of nodes, and therefore, the size of open grows linearly. On the other hand, breadth first search uh, finishes one level before going to the next level. So, we have already seen this, right. At level 1 there are 1 node, then there are 3 nodes, then there are 9 nodes, and then there are 27 nodes essentially. What is breadth first search doing? It multiplies by B. As it goes down every level, at every level initially it was 1, then it became 1 into 3, then it became 3 into 9, then it became 9 into 27, and as you go deeper it multiplies the number of nodes, and you know that if you keep multiplying this, then that is where the exponential growth comes from essentially. So, as far as the size of open is concerned, depth first search is definitely a good algorithm. The space required is only linear in nature, whereas breadth first search will always require exponential space. So, that is a negative point for breadth first search. And in fact, as I mentioned earlier, as the search sweeps from left to right, the size of open keeps decreasing for depth first search, because we have finished all those nodes in. So, initially for example, we had 4 nodes here, and then eventually when we backtrack and come back, there will be only 1 left essentially. So, the size of open keeps also decreasing. What do the search frontiers look like? By search frontiers we mean the open nodes, because they define the set of candidates that you want to inspect. The frontier for depth first search, as shown by the pink nodes here, grows linearly. We have seen that it adds a fixed number of nodes at every depth, whereas the frontier for breadth first search grows exponentially, and that also we have seen essentially. That is shown by the yellow nodes essentially, and that is in some sense a measure of space complexity. So, let us compare the two algorithms on 4 parameters: time, space, quality of solution, and completeness. We have already seen that time complexity for both depth first search and breadth first search is exponential. So, they are equal in that. So, remember that time complexity we are measuring as the size of closed, and space complexity we are measuring as the size of open essentially. These are just estimates. When it comes to space complexity, we see that depth first search is the clear winner. It only grows linearly, whereas breadth first search grows exponentially. In terms of quality of solution, there are no guarantees by depth first search. It may find a path which is longer, as opposed to breadth first search, which will always guarantee the shortest path, because it is always generates a node closest to the source first essentially. So, whenever it finds a goal node, it will find it at the shortest distance from the start place essentially. So, that is a plus point for breadth first search essentially. What about completeness? By completeness we mean that if a goal node exists, or if a path to a goal node exists, then will it will the algorithm find it. That is what is our notion for completeness. So, we also use the term systematic sometimes for this. And by systematic, we mean that will it explore the entire state space eventually, which means that, in other words, what this would mean is that if there is a path to the goal node, will it find it. Now, if I give you a graph which is something like this, S A, just a trivial graph, C D, and let us say there is a goal node which is not connected to any of these nodes essentially. So, this is a situation of no path to goal node. So, obviously, whatever you do, you can't find a path to the goal node because there is no path to the goal node. But when we talk about completeness or a search being systematic, what we mean is, will it systematically explore the entire space? By this we mean, okay, it looks at the node S, then it looks at the node A, then it looks at the node B, then it looks at the node C, then it looks at the node D. It has seen all the nodes that can be reached, which are reachable from S. The entire graph which is connected to S, it has explored, and if it does that, and only then it will say that I can't find a path to the goal node. So, it can report failure essentially. So, the corollary of this is that completeness means that if there is a path to the goal, will the algorithm find it essentially. And we have already seen in that small example that depth first search could go down an infinite path, especially if the search space is infinite essentially. Whereas, if there is a path to the goal node, and we have already seen this earlier, then breadth first search will find that path because of the fact that it looks at paths of increasing length essentially. First, it looks at paths of length 0. If the start node itself is the goal, then you can return that. Otherwise, it looks at the first level nodes, paths of length 1, then it looks at second level nodes, paths of length 2, and so on. So, if there is a path, and if there is a path, it means it will be a path of finite length. Breadth first search is guaranteed to terminate with the path essentially, whereas breadth first search is depth first search is not guaranteed to do that for especially for infinite graphs. So, you can imagine infinite state spaces, for example, number systems will have problems which have infinite nodes because there are infinite numbers, and you are looking for some numbers with certain properties, maybe numbers which satisfy which do not satisfy Fermat's last theorem. Are there 3 numbers such that the Fermat's last theorem is not true for them, or something like that. The search space is infinite, and if there are 3 such numbers, then depth first search may get lost into an infinite path, whereas breadth first search, being conservative, will find that path. The condition is there must be a path of finite length from the start to the goal node essentially. So, for example, if there is an infinite search space and the goal node is here, this is the example that we had seen earlier. Depth first search will just go down some path here and keep going down this path, and it will never find the path to the goal node. So, it is not complete, it is not guaranteed to find the path if there exists one, whereas breadth first search is guaranteed to find a path if there exists one. So, our next
Sir, one doubt. Yeah. So there are 2 factors for this difference, right? One is finding the path, and one is whether the search space is infinite or not. Yeah. So for depth first search,
see, if the search space is finite, okay, then both algorithms will explore the entire search space and say that path exists or does not exist. Okay. Here is a small example. This is the start node, this is the goal node, this is A, B, C, D, let us say. In this case, there is a path to the goal node. So, if that G node was not there, the G node was separate as drawn on the top, then both will explore that S, A, B, C, D, and both will say no path. That is for the case of finite this thing. Even in the case of a finite graph, for the one which I have drawn here at the bottom, breadth first search will give you the optimal shortest path. Why? Because it will look at S first, then it will look at A, then it will look at B, then it will look at G. Whereas, what will depth first search do? Depth first search will go from S to A, from A it will go to C, from C it will go to D, and from D it will try B, and then it will try G. So, it will find a path S, A, C, D, G. It will give you not the shortest path. So, that is a third property, quality of solution. Breadth first search guarantees the shortest path. Breadth first search, as this example show, will not find the shortest path. In the case of infinite search spaces, if there is no path to the goal, then both will go into an infinite loop, because they will keep searching. But if there is a path of finite length to the goal space, then breadth first search will find that path, because it goes down level by level essentially, and because the goal node is at some finite level, finite distance away from the start, and breadth first search will eventually look at that. Whereas, depth first search, as shown in the middle diagram here which I drew, can go down a path and never come back from there. So, both algorithms have their advantages, and the fact that we are fighting against exponentially growing trees is not something that you should take lightly, and which is one of the reasons that some of the algorithms that we will see will try to address that issue, that can we work with smaller space complexities and time complexities. But for the moment, we will turn our attention to an algorithm that uses linear space for open, which means it got the good property from depth first search and guarantees the shortest path, which gives a good property from breadth first search. Is there an algorithm which combines these two things? So, I will ask you to think about this, and we will take this up in the next session.